Hi and welcome back to my channel. Today I'm just going to briefly look at power supplies for vintage radios. If you work on old radios or you collect old vintage radios, you'll find that there's all sorts of different batteries, some of which you can still get, some of which you can no longer get, some of which are rather expensive. So I'm just going to have a brief look at some of the ways you can get around this so you don't buy all sorts of different batteries and accidentally leave them in radios. The first one I have mentioned before in one of my other videos. This is a Roberts radio which originally ran on 2 lantern batteries, and they are 6 volts each. So one was on this side, one was here, and the 2 6-volt batteries connected in series would give you 12 volts. So the radio is designed for 12 volts. And my solution was to not modify anything in the radio itself, just to add on, solder into where the positive and negative leads, this battery holder, which takes 8 AA cells. So you get 8 AA cells in there, will give you approximately 12 volts. And then I bought a charging unit and chargeable batteries. So these are the chargeable batteries, and there are 4 of them on charge. Unfortunately, I can only do them 4 at a time. I think you can get chargers that will do all 8 at once. So when those are charged up, I put the other 4 in, and it runs for a long time on those. It's been used for quite a few hours since I charged it. This is the first time I had to recharge it, and it's been used daily. So yeah, I must have put on quite a few hours. I don't know exactly how much. But it's certainly a solution that enables you to use the radio in the way it was intended, as a portable, without having to buy the expensive batteries. I think the original batteries probably cost roughly the same as this charger and the rechargeable cells with it. So having used it once, I've probably got my money's back, and hopefully these cells will recharge many times. So that's one solution. And again, if you've got a 9-volt radio, you can get one of these that takes 6 batteries and do the same thing to give you 9 volts. So that's that one. Now the other one is the Hacker, and this takes 2 9-volt batteries. It's an RP30. Not all the Hackers take the same batteries, but this one takes 2 PP9 batteries, which gives you 18 volts. Now that means rather a lot of AA batteries if I was to use rechargeables, but for this one I built myself a little power supply here. I'm not going to show what's inside. It's not built to the best practice. It's just something I cobbled together out of odd bits. So that is very straightforward linear power supply. Now you can't really use switch mode power supplies with these things because they kick out so much RF noise that on medium, long wave and short wave they will actually wipe it out, and you'll get virtually nothing but noise. So you need a linear power supply, and a linear power supply has far fewer components anyway, and it's reasonably easy to make one up. At this point, I would say don't work on high voltages unless you're trained to do so and know fully what you're doing. My videos are only for entertainment. They're not for tutorials, and therefore don't copy anything I do here. I'm just showing what I did, and my training was so many years ago, and I haven't worked in this line for 25 years. So there we go. My safety knowledge of safety procedures and so on will be out of date now. So that basically is the power supply I've devised for that. So I'm just going to go briefly through it, because the same sort of power supply can be used for different voltages according to the regulator you use. Now I found this transformer, which I used in that supply, which came from a Hornby train controller originally. So it gave out 16 volts AC approximately, from the 240-volt mains. So I had a fuse coming in, and the easiest way to do that actually is to you can get 1 amp fuses that will fit in the plug. So I stick one of those in the plug. That's the simplest way. That goes to the mains winding. The core of the transformer I've connected to earth, and also obviously through doing that it also connects the whole case around this power supply to earth, which gives it shielding from any noise, and it makes it much safer because it's at earth potential. If something went wrong in this transformer or any mains parts touched the case, it would go to earth and it would blow the fuse. So you need to have a low fuse. It's no good having a 13 amp fuse in there. You want a 1 amp ideally. 3 amp fuse is more commonly available. So anyway, after this transformer you get 16 volts AC. Now here's a bridge rectifier circuit. These diodes are IN 4007s and they will take 1 amp. So also when I come onto it, the regulator trip is also rated at 1 amp. So you can't draw more than 1 amp from this supply because it would destroy the components. So that's worth bearing in mind. This is all right for a transistor radio, which should only be taking a few milliamps. So bear that in mind. If you want to design something that will drive something that needs a bit more power, then this circuit won't work unless you beef up these components and you need to do something else after the regulator, maybe drive transistors or something that can handle the current if you want a higher current supply. I've also drawn in here a fuse which could be a slow blow fuse, quite a low current value. Maybe make that a 1 amp fuse. Then if you try to draw more than 1 amp, this would go and protect this circuit. Now, as I say, the one I got over there I just cobbled together for my own use, and I wouldn't dream of passing that on to anyone else. The way this works is, if we look at in terms of conventional current flow, when this side is positive, because this is alternating current, so it alternates between positive and negative. When this side is positive, it will go through that diode to the positive terminal over here. When this side is positive, it goes in here and through that diode out to here. And the same applies when this is negative through there to negative. When this is negative, it goes through there to negative. So that means that it's always positive here and always negative here. But it would be all humps and bumps, if you see what I mean. If you imagine that here you've got AC coming in, and here you would have a lot of humps and bumps like that. So that wouldn't be very good. It would make a buzzing noise on the radio, quite a loud buzzing noise. So you put a capacitor across, which means that it's slowly discharging, so you do get a tiny bit of ripple, but it does smooth out the power. You charge up the capacitor when it's up here, and it supplies current when the incoming voltage is down here, so it smooths it out. Now what I've done is I've added resistors across. I don't know what value to use. I just stuck in 10Ks because I had them, but just something to drain this down, otherwise this will stay charged up for some time after the power's taken off. So I just think it's quite good practice to put a resistor across them, which takes, in a few seconds, the voltage, which is quite low anyway, will die away. Now, after this rectifier and this capacitor, the voltage here across this is actually 25 volts. I measured it. So it's a good idea, because this capacitor is doing an awful lot of work, to use one considerably higher rating. So I've put in here one rated at 50 volts. So this is a good capacitor. It's quite large. It's 1000 microfarads, 50 volts. So that smooths out the supply quite well. And if you had a radio that ran on 25 volts, you could run it from here. it would probably have a bit of a buzz on the in the speaker, but it would work. But really you want it nice and smooth. Now the best thing to use is one of these regulator chips. Now I've got a whole selection of them here, and I won't try and open it because they'll all fall out and go everywhere, but they basically have got 3 terminals on them, and they have the number, most of them have the number 7, 8, and normally it's LM7. I think these are copies, so they're not probably the ideal ones to use, but they do work. There'd be an LM7805 will give you 5 volts regulation, and you tend to get through a lot of those because a lot of things use 5 volts. There's a 6 volt one. Some radios are 6 volts, so you could make a supply using a 6 volt one. 8 volt, I'm not going to likely to use many of them unless you wanted to run a 9 volt radio a little bit under voltage, save the components a bit or something. There's the 7809, which is the one I used in the Grundig power supply in one of my other videos. There's a 10 volt one, 12 volt one, and the 12 volt one again is something you probably use quite a few of. 15 volts. Some supplies you need plus or minus 15 volts, but you have to design it such that you can use a positive going regulator for both halves, because the negative going 15 volt regulators are surprisingly expensive. There's the 7818, which is the one I used for this supply, and there's a 24 volt one. I used a couple of those in a dual rail supply made for an amplifier. But the one we used for this circuit was this one, the 7818. So there it is, and I've labelled it LM7818. Then the thing to know here is you have the input of the chip here, the common ground there, and then the output side over here. Now, what I haven't done on this diagram is put the lining going from there to the negative rail, so we'll do it now. So that's joined to the negative rail. So the plus 25 comes in there, and at this side on the output you get plus 18. Now that is very good. I think mine measures about 1805, probably within the accuracy of that meter. So you've got about 1805 volts, and even under load or off load, that stays very stable at 18 volts. And if you look at one of my other videos for the Grundig power supply, I actually put a load on and the voltage hardly shifted. So there's extremely good regulator chips. Now, the other thing you must do is put small capacitors between the input and the output lines going down to the common. These need to be as close to the chip as you can make it. And I've used 10 nanofarad ones, and they're little tiny ceramic ones, so they're not big, but they need to be as near to this chip as you can get it. And as a general rule, when you're using integrated circuits, whether they're audio amplifiers or logic chips or regulators like this, you should always decouple the supply rails that go into them with a small capacitor, because you can get oscillations that you don't want. You can get all sorts of problems. I built an amplifier and I had these too far away from it. They were fitted there, but they were back here across these capacitors, and it was no good doing that. And fortunately I brought the amplifier up on a variac slowly, and the dim bulb lit up, and I knew something was wrong. So I took the power off quickly and found it was oscillating, and that's why it was going wrong, and it was taking far too much power. So yeah, a little thing to learn there: decouple power supply rails to integrated circuits. That's a good practice always to do that. And they're only, say, little 10 nanofarad ceramic capacitors, so they don't cost anything to speak of really, just pennies. So anyway, out of the chip, you've now got 18 volts, and this is a really nice smooth supply. It's just like a battery. You know, you can put it on an oscilloscope and you'd see hardly any ripple on there. And just to make sure, I've got another capacitor. It's probably a bit big, but I've put a 1000 microfarad capacitor there, but it's rated at 25 volts now because we're safe. We're down to 18 volts, and it's not going to be doing that much work. It's just to make it sure it's nice smooth supply and smooth out any transients that you might get when you switch it on and so on. Again, I've put a few K resistor across it just to drain the power from it. And then you got the 18 volts DC supply that you can connect into your radio. So that works very well. And I won't show it now working because I've got these things here, and these are switch mode, and they put out a huge amount of noise. But that's one way of powering one of these. And I found another way which I use is to use two of these little PP3 size batteries and connect those into the radio. It will run for a little while on those. It's okay for if you want to use it briefly or just demonstrate it or work on it, get it going. But they won't last very long because they're tiny batteries compared to the ones that should be used in it. But I hope that's helpful anyway. The point I'm making really is that this sort of power supply can be adapted. And I didn't think there was much point in going through demonstrating the one I've just built after I'd already demonstrated the 9-volt one for the Grundig in another video. But you can always alter these to get the voltage you want, depending on which regulator chip you select. And as I say, you get a whole box of them like that, and it's not terribly expensive. The other thing to remember is they got the 3 legs on them, but also the tab on them is connected to the common ground as well, which sometimes you can make use of if you don't want, or you having the case negative. Well, the other thing I haven't mentioned is when you build one of these supplies, that needs to be fixed to a heat sink of some kind. As I built mine in a metal case, I just screwed it to the side there. Inside there's insulating washers, there's a mounting kit there which enabled me to mount that inside there onto this case with a little strip of board with the other components on it. And basically that ensures that this doesn't really get hot at all. That certainly doesn't get hot at all running this. The transformer does warm up after a while. That's due to eddy currents in the core. That would happen with any transformer, but yeah, there's no heat problems here. And I think these regulators will take a small current without a heat sink, but it's good practice to have some sort of heat sink on there. So anyway, I hope that might be helpful to some, and I've gone on a bit longer than I meant to. This is quite long for me in one of my videos. So if you're still watching, thanks very much for watching, and goodbye.